Okay, so let's get started. So any question from this time? Let me sure everything is correct. Okay, stream seems to be working, and this is working. Okay, so any question from this time? Oh, wait. Do we have an echo? No. Maybe. Hello, 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 hello. Maybe turn the volume down. Okay. Like this. Okay. Yeah, this time we go through. Well, we start talking about quantum mechanics, and why do I don't have a pen? Actually, can you? Okay. 可以去帮我拿笔吗？他没有拿。Okay. Yeah. Yeah. This time we go through the quantum mechanics. So we have a simple postulate saying that quantum state is a unit vector, and then when we change a quantum state, we need to rotate it by a unitary matrix. And then there is a weird thing about measurement. Okay, so in our simple version of postulate of quantum mechanics, we say we do computational basis measurement. So we think about our quantum state can always express in computational basis. So that's the most standard basis you think about. Just like when you write these columns, so we write this column, and every number corresponds to the coefficient of the computational basis. And so when you do a quantum measurement, two things will happen. First, the state will collapse into the computational basis state. So this computational basis state, usually we think it as a classical state, so correspond to some classical information. Maybe it's a bit, then it's 0 or 1. And but this collapse happens with probability AI squared. AI absolute squared, and the AI is the coefficient to the basis I. And the observer will know which I this happened. Okay. And also, hey, when you have multiple systems, then you tensor product all their Hilbert space together. Okay. And we talk about there are 3 different types of measurement people will talk about, and actually 4. So the first one is the computational basis measurement we just said, and then second one is you can rotate it to change your basis, so you can actually measurement against any orthonormal basis, and so you just replace this AI to whatever coefficient in your orthonormal basis. Then we say we can measure against a Hermitian operator. So this is basically just measure against orthonormal basis, but for every basis element you associate with some real number correspond to physics quantity. But so the easy way to see it is this, but there is extra complication in that there can be degeneracy. So some of the VI can have the same excuse me. Some of the VI can have same eigenvalues, and when you measure them, you cannot actually distinguish VIs with the same eigenvalue. So you project it into this degenerate space instead of projecting into the eigenvalue. Okay. So for example, like this, you have this vector 1, 1, 1, and then you project it into the subspace of the second spanned by the second and third computational basis. Then you become this vector 0, 1, 1, and then you need to renormalize your state into a unit vector. And yeah, so that's the physical measurement. And finally, there is a generalized measurement that's the defined set of matrices, whatever matrix is Mi, and they satisfy this completeness relationship. Some I and Mi take Mi equal to identity. This will guarantee that your measurement probability is equal to 1. And yeah, and the post-measurement state, you kind of think of it as this Mi times phi. And so you have a probability of getting this. That's just a known square of this thing. Okay. And yeah, And the actual post measurement state, if you renormalize it, you just divide this thing by its norm. So then this is a unit vector. Okay? Question? Otherwise, then yeah, let's run we'll do the book version of the postulate of quantum mechanics. So this is in chapter 2.2 of the book. And basically we do the same thing again, but writing a measurement in the generalized measurement. Okay? Okay. So postulate of the quantum mechanics as written in Nielsen and Chang. So first postulate, we associate with every isolated physical system. Associate with every isolated physical system is a complex vector space. And so later we'll see that this isolated is actually important. But anyway, so you want to think about the system is isolated with everything else, so it has no interaction with other place, and then you describe it with this complex vector space. So complex means the coefficients are complex number, and this vector space is inner product. Okay, and we also call this space. Okay. Oh, maybe use this. Okay. And we also will call this Hilbert space for basic historical reason. I guess. So more precisely, you should call it a Hilbert space. This is some mathematical definition, but this matters only when your dimension of the dimension of the vector space is infinite. Then because when you have infinite dimension, then you need to deal with the infinity. There can be troubles associated with the infinity, and one way to normalize them is define the Hilbert space. But anyway, in our course, we think our vector space are finite dimensional, so you can just call them vector space, but also we'll call them Hilbert space sometimes, because this is what the physicists like to call the associated vector space with your system. Okay, so Hilbert space is this vector space associated with your physical system. And so you have this vector space, and we haven't talked about in physics. So physics is saying that all the information of your isolated physical system is described by a unit vector in this Hilbert space, or this vector space. Okay. And this vector is also called the quantum state because it has all the status of your system. Okay. So every possible information about the system is described by this unit vector. There is no extra information. Okay. This is quite important, as we'll see an example maybe next class. Okay. Okay. And this vector usually will write as the bracket notation we have. So it write as a ket vector. So usually we'll see this ket side. So for us, so mathematically, this is just a finite dimensional column vector. You can think of it as this. Okay. And a small point here is that all unit vectors are also valid quantum states. So this is this small extra thing we write here. This is basically a superposition principle. So we say we will take a linear combination of any vector and normalize them. Then linear combination of all your quantum state. Then and normalize it. Then is still a valid quantum state. So this is a superposition principle saying that any unit vector is a valid quantum state. Okay. And okay. So those are status, and in physics we want to study how things change with time, and in computer science we also want to study how things change when your computer goes forward. Okay. And so how they go forward is the change between different time steps is described by unitary transformation. Okay. and this unitary transformation for us is just a unitary matrix, a finite dimensional unitary matrix. Okay, and so for example, our state was we were in some psi at maybe tan t, and then our state changed to some psi prime in tan t prime. Then this psi prime will be some unitary times your state psi. Okay. And recall that the matrix is unitary if and only if u dagger u equal to identity. Yeah. And so we have some two-star rule that we won't use, but you might be a little interested. So if you care about continuous time evolution, so how the state evolves through all time steps, and in physics there is this famous Schrödinger equation, and this differential equation says that h bar dψ dt equal to h of psi. Okay, so we have a little abuse of notation. So this is not a Heisenberg matrix. This is some Hermitian matrix, and it's called the Hamiltonian of the system. So this is h depend on the system, and usually correspond to the energy of the system. And so given this h, then you can solve how this psi evolves through t by solving this initial value problem, etc. But anyway, so our time is discrete because we are computer scientists, and we we think about our system evolves through clock cycles. So yeah, so our system goes through with circuit and gates, and those gates are discrete things. So we just apply one unitary to our state, and it will go. So the system goes into next time step. Then we apply another unitary, go to another time step. So very discrete thing, and we will not solve the Schrödinger equation. But yeah, this is just for your education. Okay. So that's how the state evolve. And finally, we have this weird thing that never happened in classical mechanics. So there's a measurement you can do on a system, and this is how you get classical information out of a quantum system. So when you do a measurement on a system, well, first the measurement is described by this set of operators mi, and those mi are really arbitrary. They only need to satisfy the sum mi dagger mi equal to identity. And we have this I here. So this I is the indices. Is the indices labeling different mi. So maybe this set have 3 elements, then you have n1, n2, n3, then I equal to 1, 2, 3. Okay, and those indices will always also correspond to different major outcomes. Okay. So you have I equal to 1, 2, 3, then you have 3 different possible measurement outcomes. Okay. So, so what happens when you measure a quantum system? And so you measure a quantum system in a state psi get psi with this set of measurement operator mi, and then one and only one measurement outcome will happen. Okay. So one of those I will be pick as a measurement outcome. And a little peak with probability, and we are using a little different notation. Okay, so there will peak with probability p of I, okay, p of I, and okay, so we just so this is a notation. We say the probability is p of I, and p of I can be calculated from mi and psi as this. So it is psi, mi dagger, mi psi, and it's just a known square of this mi psi vector. Okay. And you can easily check that the sum of probability should equal to 1. That's guaranteed by this completeness relationship. Okay, so we are good. Probability is equal to 1, and the probability is positive because this known square is positive. And yeah, I guess I should say learn here. Okay. Yeah, we learn the table. Okay, and yeah, when outcome happen, then you will know it happened, and so the people doing the measurement will know the label I. The observer will learn the label I, and also finally the most weird thing that never happened in classical system is when outcome I happen, then the system collapses into this, will collapse into state. So it will collapse into this state basically MI side but renormalized. Okay. And this is something so this is done kind of permanently. So once it happens, then it happens. Then your state is changing into this MI side. And yeah. So if you want to change it into other state, then maybe you do a measurement to get into another state, or you do a unitary to get into another state. But from this time forward, after you do a measurement, whatever operation you do, you are doing on this MI side. This system is already changing to this MI side. Okay. And this is a weird part, and we'll see some example of this later. And finally, we have this force property excuse me, that says that when we have multiple systems with Hilbert space H1, H2 to Hn, and we're thinking they interact with each other, then the composite system, the Hilbert space is H1 tensor H2 tensor to Hn. And this is why we need to talk about tensor product. Okay, and I guess a quick example. You have a bit, a qubit. I guess we will see this very quick. A qubit has H1 being two-dimensional. Span, I guess 0, 1, right? And actually all the HI span 0, 1. And then if you have like a H1 tensor H2 tensor H3, then is a span of 0, 0, 0, 0, 0, 1, da da da. So all 8 possible 3-bit strings. Okay. And yeah. So that's the example of how, I guess before we go to example, any question about the theoretical formulation? If not, okay, then let's go to example. And as we said, the easiest possible example is this two-dimensional space C2. And well, yeah, this is non-trivial. Obviously, you can have one-dimensional, but it's really trivial. There is no information inside. And so you have the two-dimensional space C2, and it's a qubit. It's the quantum equivalent of 1 bit in classical computer science. And then your state will be, well, it's a two-dimensional vector, so it's on AB, and AB is a complex number. And you can also write it in basis form, so A of K0 plus B of K1. And we say it must be a unit vector. That means this A absolute value squared plus B absolute value squared should equal to 1. And so there are quite a few examples. So this parts vector we have defined when we talk about polymatrices. This plus and minus vector, the eigenvector of the x of the sigma x. But anyway, the plus vector is 1 over square root 2 0 plus 1, and the minus is 1 over square root 2 of 0 minus 1. So if you write in this form, it is 1 over square root 2 1 1 and 1 over square root 2 1 minus 1. And also we have the 0 and the 1, and so 0 is just 1 0 and 1 is just 0 1. Okay, this is computational basis. Then we have unitary transformations on a qubit. So there are 2 by 2 unitary matrices. And example of them are those polymatrices. For example, this x equal to sigma x is 0, 1, 1, 0. And these actually correspond to classical NOT gate. And why do we say it's a NOT gate? Because we think about those 0 and 1 are considered computational basis. So I think this 0 kind of correspond to classical bit being 0, and this 1 correspond to a classical bit equal to 1. Then when you apply x on 0, then it becomes 1, and then you apply x on 1, it becomes 0. So it flip that bit, and that's not gate do, right? Not gate will flip a bit. Okay. And but then if you apply x on plus and minus state, then interesting happen. We say that we know that as we claim x, these plus minus state are eigenvectors of this x. And when you x apply a plus, you actually get to plus back, and you can kind of see it from those those equations we just talked about. So we know x will flip between 0 and 1. So if you flip 0 and 1 on this 0 plus 1, then nothing will happen because 0 plus 1 is 1 plus 0. Sorry, 0 ket plus 1 ket is 1 ket plus 0 ket. And when you apply on minus, then a weird thing happens. You flip 0 and 1 here, then it becomes, so 0 minus 1 become 1 minus 0. And that's basically the same thing, but you get the extra minus sign. So see that x on plus, so the minus state is a negative 1 eigenstate of this x operator. Okay. And finally, we do measurement. Okay. So I've talked about measurement before, there are a lot of measurement, but now we do everything in this more generalized, more formal language. That seems actually a bit overkill. Yeah. So now we try to do computational basis measurement. Okay. As we say, as we say from just a review, when you do computational basis measurement, you should just get a 0 or 1 with probability a squared and b squared. But now we try to write computational basis measurement in a very complicated way, in a generalized measurement notation. Okay, so we do computational basis measurement. Okay, computational basis measurement. So I just write this to get you familiar with the generalized measurement notation. So generalized measurement should describe by a set of m. And there are two m here because there are two possible outcomes, 0 and 1. And so m0 is this projector onto 0, and m1 is this projector onto 1. So ket0 bra 0, ket1 bra 1. And then you can check that this is actually a projector. Okay. Yeah, let's do this again, although we have done this. So for example, so obviously m0 dagger equal to m0 because you swap those two, then you get back to yourself. And if you do n0 square, then you have 0. Okay, wait, do we have this somewhere? No. Okay, so we also have 0. Okay, 0. These things multiplying together, and the middle one is 1 equal to 0, 0. Okay, because this is 1. Okay, so we check the projector once again because the square of themselves equal to them, and also their Hermitian, although usually, yeah, so they are Hermitian projectors, although we sometimes omit the Hermitian. Yeah, we usually omit saying Hermitian in this course, but I think all the projectors in this course we talk about Hermitian. And anyway, they are projectors, so this m0 plus m1 is this 0 projector plus this 1 projector. So I should say 0 projector and 1 projector, and this is equal to identity matrix. Okay, and okay, so we checked out the completeness is satisfied. We want the sum mi dagger and mi equal to identity. And how about we apply this 0 state? Then, okay, and as we said, the post-measurement state should be mi on your state side. Okay, so the post-measurement state corresponds to this m0 is m0 0, and so it's still 0 because, well, yeah. So you apply this on 0, you get back to 0. And Your state is you project the 0 kate onto 1, but 0 and 1 are orthogonal, so this is just a 0. Okay. So there is a little ambiguous. So okay, not really ambiguous, but there is something to be careful. So the 0 is not a 0 kate. The 0 is a vector of length 0. So it's just this kate of 0, 0. But anyway, so we see that the post-measurement state of measurement on 0 has length 1. So you have 100% probability to get a measurement called 0. So this 0 corresponds to this 0, 1. There are a lot of 0 here. And your state will collapse back into the 0 kate. And well, you start with 0 kate, you collapse into 0 kate, so you don't really change your state. Okay, let's do a more interesting example. So we do M0 and 1 measurement, basic computational basic measurement on this plus state. And we know plus state is this 1 over square root 2 plus 1 over square root 2. So you kind of expect 50%, 50%. But let's go through the more complicated math. So N0 on plus is 1 over square root of 0. And N1 on plus is 1 over square root of 1. Okay? And then the probability of getting the 0 outcome is the known square of this N0 plus. And then that's this 1 over square root square, so that's 1/2. And the probability 1 is the known square of this thing, so that's over 1 over 2. So you see you have a 50% probability to get outcome 0, and that's collapsing into 0, and a 50% probability to get outcome 1, that's collapsing into 1. Okay. And hopefully you see that this just correspond to computational basis measurement. Okay. Any question? And I guess I can write a little in more matrix notation, so it's a little clearer. So once again, plus is so the plus state, just as a way to hopefully make you more comfortable with this. So what we are doing is plus state is this 1 over square root 2, What's going on? Oh no. Microsoft Edge is crashing. Oh, okay. It's back. 1 over square root 2. And yeah. And this M0 is this projector onto 0, so it is 1, 0, 0, 0. And M1 is 0, 0, 0, 1. And M0 plus is just this 1 over square root 2, 0. And M1 plus is 1 over square root 2. Oh, sorry. Is 0, 1 over square root 2. Okay? 0, 1 over square root 2. So this is what happens when you write down all the matrices. Okay? And finally, we have this I guess we didn't make it too rigorous, but I think it can be made rigorous. But we have this intuition that amplitude squared and to absolute value squared equal to probability. So we say that our state in our physical system should be a unit vector, and this length being unit correspond to, so unit vector is something with the length 1, and this length 1 correspond to the total probability of your system should be 1. Okay, and what's the total probability of system? Your system are just yourself. But anyway, the probability has more sense because we think and yeah. But anyway, so we say that our system must be doing unitary transform because they preserve the total probability. And okay, so why we can say total probability, because we will be thinking about measurement. Okay. So when we do measurement, we can kind of think about those subnormalized state as state associated with some probability, and so we can kind of think about our state turning into this subnormalized state, and we know the probability of getting this state is the non-square of it, and so for example this thing and this thing, and so we can kind of write this subnormalized state as probability times your state. Okay. And so you want to see your actual state, and you normalize it back to the unit vector, and you can calculate the probability by seeing its non-square. Okay. And yeah, so sometimes it's useful to write normalized state as subnormalized state as probability times square state. As you see, the last day is we have a much nicer form is mi psi instead of those ugly expressions where we ask probability is this thing and then your collapse state is this thing. Okay. So those are more complicated notation, but you can remember that you can calculate them from just this mi psi. The probability is this non-square, and you can renormalize it by dividing the square root of probability. Okay. Okay. So that's example of measurement now. And disclaimer here, once again, we will deal with discrete and finite time space. So our space, basically the vector space is, so we mean, like the vector space is not discrete, but we mean the dimension of vector space is finite. And and also our time steps are just discrete set of points, because we think about our system is in a circuit model, and we'll apply gate by gate. So there is some kind of class cycle of your computer. Okay, and this will make things a lot easier than the infinite dimensional space things. But we can still do a lot of computation with these discrete and finite systems. Okay, and then a little bit of physics. So there is this measurement problem we talk about. We touch this a little about, but we can say this again. So we say that in our mind, we think about the world has a classical part that's basically U, and the normal world you see, and there is this quantum system that is described by this quantum state. And if you do measurement on your system, you can get classical information out, and it will collect your quantum system to whatever mi psi probability. Okay, and now the weird part is you have classical observer, because we say every physical system should be described by the quantum mechanics. Then yourself should also be is also a physical system, so you should be described by quantum mechanics. So why do we have this weird line here separating quantum world and classical world? Okay. And yeah, so there are actually multiple problems here. So the first problem is why do you look classical? Why don't you feel superposition everywhere? And this problem actually have some explanation, and yeah, there are ways to make this kind of rigorous to say why does the system behave kind of classically, okay, in this macroscope world. And but there is another reason is where do you draw a line? Okay, because you really feel yourself is classical, you don't think yourself is superposition or something. Okay, and yeah, and this is really the measurement problem. And so when you try to remove this line and make it yourself the observer also quantum, that a lot of weird things happen, and maybe you have that's where people get the many word interpretation, etc., etc. But anyway, here we take this more practical approach, although these things not very satisfying as a physicist point of view. It's not unifying, but we can, in practice, you can draw a pretty clear line here because most of the words still seems pretty classical, and you can say your small quantum system is a quantum system. Okay, so we kind of avoid this question of just not looking at it with this, and we just adopt this not very elegant worldview, but it works. Okay, now let's talk about something that we can we can compute more rigorously, and that's this quantum indistinguishable problem. Well, and this is a quantum phenomena coming from our measurement rule. Okay. And that's the thing. And this phenomenon is that some quantum states are not perfectly distinguishable. So what do we mean by perfectly distinguishable? So first we give an example of a perfectly distinguishable state. So we see that orthogonal states are perfectly distinguishable. Okay. So for example, we have a state K0 and K1. And what do we mean by distinguish? We mean that there is a measurement. So there are two of them, and we give a two outcome measurement distinguish. So we can distinguish them by this computational basis measurement 0, 0, and 1, 1. And what do we mean by distinguish? We mean that when we do this measurement on those two states, okay, and so each state can have two possible measurement outcome, but they are perfectly distinguished. So this 0 state can only get this 0 outcome, and this 1 state can only get this 1 outcome. Okay, that's perfectly distinguished. And oh, this is a little ugly, so let's change the color. Okay. Okay, so maybe let's do this color. Okay, so we mean this 0 state when you do those measurements on those two possible states. And when your input state is 0, you always go to 0. And your input state is 1, it always goes into 1. Okay. And similarly, what about plus state and minus state? And if you try to measure them in computational basis, you cannot distinguish them because, as we say, so our small example here, we see that when we measure, where is it? Should be somewhere here. So we measure the plus state in 0, 1 basis, then you get 50% 0, 50% 1. And similarly, you measure minus in 0, 1, you get 50%, 50%. So it's totally not distinguish anything. Okay, but you can measure in different bases. You just measure the plus basis and the minus basis. And once again, is your 100% give you this plus outcome, and 100% give you this minus outcome. I guess, yeah. Our notation is a bit tricky. We should say this is like M0 and 1 because we index it with integers, but because in our definition we always index it with integers, but it's pretty clear here, so we just say it's plus and minus. Okay. And I guess I can just I guess we can just extend our I to be whatever state. Okay, so I in some whatever alphabet state. So our I is now plus and minus. And anyway, so that's what we mean by perfectly distinguishable. So you have some state and some measurement, and one of the state will always give you one of the measurement outcome, and every state give you different measurement outcome. And but now we see not perfectly distinguishable. So non-orthogonal states cannot be perfectly distinguished. For example, this is 0 state and this this 0 state and this plus state. They cannot be perfectly distinguished. So, for example, say you want to distinguish them with this 0, 0 and 1, 1 measurement. Then you do this measurement and you have a 0 outcome and a 1 outcome. And so 0 state, once again, just like here, you will have 100% give you the 0 outcome, and 0% give you 1 outcome. And the plus state give you 50% 0 outcome and 50% 1 outcome. And but if you just want to have one copy of them, okay. So here we should say here something. Recall state collapse after measurement. Recall state collapse after measurement. Okay. And yeah. So once you do the measurement, then you just going to get a 0 state or a 1 state, a 0 state or 1 state, no matter what your starting state is. So even if you start with a plus state and you get 0, then you just get 0. Then you do 0, 1 measurement again, you just keep getting 0, 0, 0, 0, 0. So only drawing on these 50%, 50% ones. Okay. And you get 1, then you keep doing computational measurement, you get 1, 1, 1, 1, 1, 1, 1. Okay. And obviously you get 0 as input, you will get 0, 0, 0, 0, 0, 0. Okay. And anyway, so what does this mean? So we are going to see these 0, 1 once. Okay. And so if we don't know about, so we kind of don't know about the input here, we kind of, so we kind of cover this up and we just do the measurement and see the outcome. So then when we see the 1 outcome, then we know that it cannot be the 0 state because it's 0% getting 1. So you see the 1 outcome, you know that you come from the plus state. Okay, so that sounds kind of nice. But you see the 0 outcome, you don't really know which one of the state come from. You might come from a 0 state, then you will get 0. But you can also come from a plus state that draw on this 50% probability, then you get this 0. Okay. So yeah, so you cannot distinguish the 0 and the plus when you see ket 0 outcome, say. Okay, and but you can say that this is just happen when you do computational basis measure, and what if you do other basis, maybe that's better. So if you do plus minus basis, then similar thing happen. So if you do plus measure. I guess and this is measurement outcome, so I should say 0. Okay. Outcome 0. Yeah. So if you do plus minus basis, then now the 0 state will give you 50%, 50% on the plus minus, and the plus state will give you 100%, 0%. And once again, you see a plus outcome, then you don't really know it comes from a plus state or you come from the 0 state collapse into plus with 50% probability. Okay. And yeah. Oh, sorry, I forgot. Okay. So as we say, the state already collapsed, so you measure again, then you just keep getting the same outcome. Okay. So I guess I will erase this. Sorry about this. Yeah. And but you might say that well, you are just doing 2 of the many possible measurements. What if you do some really weird generalized measurement here? And okay, we have 5 minutes. We probably have enough time. Okay, and yeah, and we can prove that we have 2 state that not orthogonal. So psi 1 has inner product with psi 2 not 0. Then any measurement M1 and M2 trying to distinguish them, they cannot perfectly distinguish them. So you cannot have psi 1 go to M1 with 100% probability and psi 2 go to M2 with 100% probability. Okay, so this is what we want. We want psi 1 M1 has known 1, and psi 1 and 2 has known 0, because if it is 1, it must be 0. This is by completeness. and then psi2 go to n1 has probability 0, and psi2 go to n2 has probability 1. So this is perfectly distinguished. Okay. And okay. And so we start with using that the inner product is not 0. The inner product is not 0, so we can try to write the basis with psi1. Okay. So psi2, we can write it as some coefficient times psi1 plus another coefficient beta times some vector orthogonal to psi1. Okay. So we're just doing some orthogonal basis with one of the vector being psi1. And now important thing here is alpha not equal to 0. That's using the inner product not equal to 0. And obviously, and then this is a unit vector, so alpha squared plus beta squared should be 1, and this alpha squared is not 0, so this beta squared must be less than 1. Okay. And okay, so where do we do? Okay, we go from this equation, and so we say m2, we see m2 psi2, and we expand psi2 in this psi1 and psi1 dagger equal to alpha n2 psi1 plus beta n2 psi1 dagger. Okay. But from this equation, we see that n2 psi1 is non-zero, so it's just 0, and so this is 0. Okay, so this thing is just beta n2 psi1 dagger. Now we try to calculate the non-square of this thing. Okay. And so you do inner product of it with yourself. So on the left hand side you have this, and on the right hand side you just have beta square and this n1 perpendicular, n2 dagger, n2, n1 perpendicular. Okay. And this should be less or equal to this n1 perpendicular, and so we just add another term that's positive. We add this extra n1 and 1 dagger term here. Okay. And this is a positive thing because it's the inner product of n1 is a non-square of n1 psi1 perpendicular. It's a non-square of, okay, so basically we are adding this beta square and the non-square of n1 psi1 perp. Okay, so non-square of non-square is positive, and beta non-square is positive, so this is a positive number. And yeah, so this is a positive, I guess, greater or equal to 0 number. So this can be 0 if beta is 0, but anyway, this is a semi-positive number. And so you add a semi-positive number, so this expression is larger, greater or equal to. And so finally, what do we want to add this term? We add this term, then we have n1 dagger, n1, m2 dagger, n2 here, so we can use the completeness of our measurement. So you get identity here, and then this is just the inner product of n1 dagger, n1 dual and n1 dual here. And we didn't say, but this is a normalized vector, so this is just 1. So this is beta square, and okay, so we have seen say that beta square should be less than 1. But this is a contradiction because we say this thing should equal to 1. Okay? Because this is one of the perfectly distinguishing probability condition. Okay, so we have 1 less equal. So I return this wrong, so it should be less or equal to. It should be strictly less. Okay. It is strictly less than 1, as we say. So 1 strictly less than 1 is a contradiction, so this cannot happen. And yeah, we are just on time. No, we are really slow. Anyway, any question? If not, then we'll continue this. We'll continue on this PDF next time on Thursday. Okay, I think it's time for the class. Okay, see you on Thursday.